Guys, welcome to the chapter on chemistry, specifically the chemistry of life, or how chemistry relates to living beings, or human beings in this case. As always, the chapter will begin with objectives. I'll let you guys read through these on your own, but these are the things that you should be able to do by the end of the chapter, so I would use these for studying purposes. So chemistry is the study of substances or chemicals and the interactions of these substances. So all of the different things, right, chemicals, compounds that exist in the world, and the way that these substances interact when we put them together. The reason that we study chemistry is that the body is made of chemicals, and the behavior of these chemicals determines the behavior of the body. All matter is made up of chemical elements, and matter refers to anything that has mass, anything that takes up space, no matter how small that space is, right? It can be absolutely itty-bitty, smaller than a cell, smaller than microscopic. If it takes up space, it is matter. So again, everything is matter. I am matter. The air that I'm breathing is matter. The water that I'm drinking is matter. The table is matter. Everything is matter. And matter is made up of chemical elements. In other words, we are all made up of the chemical elements. Now, an element is defined as a substance that cannot be broken down into a simpler substance. So you could say a pure substance. Right? A pure substance is an element. Now, there are numerous elements, and if you guys took high school chemistry, you probably looked at and studied the periodic table, right? The periodic table of the elements is the little table. It's kind of shaped like that, and it's got all of these little squares in it, right? And each square represents one element. Okay, so an element, carbon is an element. Hydrogen is an element. Oxygen is an element, right? It is a pure substance. You can't break it down any further. Now, an atom is the smallest unit of an element. Right? That sounds kind of confusing, but what that means is that it's just one of them. So like oxygen, for example, if the whole room was filled up with pure oxygen, just oxygen, then you could say, okay, this room is full of the element oxygen. That's the kind of substance that's present. But there would be a whole lot of oxygen if it was filling up a room, right? There would be a lot of them, not just one. If you had just one oxygen, one of them, that would be one atom of oxygen. Now, atoms of a given element are similar to each other. What that means is that if I had two atoms of oxygen, they would be similar. That makes sense because they're both oxygen, right? They would have similarities in common, specifically the number of protons, right? They would be similar size. They would have similar behavior because they're both oxygen. Now, atoms of different elements are different. So if I had an atom of carbon and then an atom of oxygen, they would be different from each other because they're different substances, right? They're going to have different size, different weight, different behavior, right? Different characteristics because they are different. Now, what's great about chemistry is that we join together atoms and they form completely new chemicals. And those new chemicals can have completely different characteristics. That's how we make everything around us, right? Because again, I said everything around us is made up of elements. And there are a limited number of elements, but we can make all this different stuff. And the way that we do that is by joining different elements together, right? We can put, for example, if I had just oxygen, right? Pure oxygen, that's the only element I had. It would be a gas. At room temperature, it's a gas. If I had pure hydrogen, okay, that's the element. If I have just hydrogen, it would also be a gas. So I have two gases. Now, if I put those together, okay, say I took two of the hydrogen atoms and I took one oxygen and I mixed those gases together, I would get something called H2O. And what's H2O? Hopefully you said water, right? And at room temperature, water is a liquid. So I took two gases and I put them together and I got a liquid, right? Completely different behavior. And we do this all the time. We combine different elements together and we create bigger things. And depending on what elements, what atoms we put in there, we can create solids, we can create liquids, we can create gases, we can create things that are really, really stable. We can create things that blow up and explode. Okay, it all depends on what atoms we're putting together or what elements we're putting together. Now, when we look at an atom, so like say an atom of oxygen, that atom is made up of smaller parts, okay? And those parts are called subatomic particles. So there are three different subatomic particles that go into making an atom. They are the proton, the neutron, and the electron. Okay, so atoms are made up of protons, neutrons, and electrons. In different atoms, we'll have different numbers of these. Okay, so an atom of hydrogen has a different number of protons, neutrons, and electrons than, say, an atom of carbon, because they're different from each other. Now, each of these subatomic particles is a little bit different. When we look at them, we're going to look at a few things. We'll look at where it is in the atom. We'll look at its size. So is it heavy? Does it have any weight or mass or not? And we'll look at its charge. Okay, either positive charge or negative charge. And you can think of that kind of like a magnet. You know, a magnet has two poles or two sides, the positive side and the negative side. These subatomic particles also might have a charge, a positive charge or negative charge. So when we look at an atom, what we see is that in the very center of the atom, there's this really dense core. This is where all of the like heavy mass of the atom is. And that's called the nucleus of the atom. Okay, the dense heavy core. And the nucleus of the atom is where we have our protons. So I'll put a P for protons, and our neutrons. So all of the protons and neutrons are in this dense core, the dense center of the atom. Then we have this area out here that's referred to as the electron cloud. The electron cloud is where electrons are, hence the electron cloud. So the electrons are out here, and they're always like moving around really rapidly. So you can think of them as like orbiting around the nucleus. Okay, so the electrons are always moving around out here in this electron cloud. That's the general structure of an atom. So let's look at each of these particles. Protons have a positive charge. So you can match up your P's. Protons are positive. So every proton that an atom has brings one positive charge. So if it has 5 protons, it has 5 positives. Every proton also has one mass unit. Mass is kind of like weight. So think of it as like the size, the heaviness of the atom. So every proton that's present brings one mass unit. So if if an atom has 3 protons, it has 3 mass units. Okay, and remember, those are all going to be here in this core, this nucleus. So the more protons, the bigger the atom. Neutrons are neutral, right? Sounds just the same. Neutrons are neutral. What that means is that they have no charge. They're not positive and they're not negative. No charge. They do have some weight though. Hey, every neutron also contributes 1 mass unit to the weight of the atom. So 5 neutrons, that adds another 5 mass units. So you see both of these really heavy things, the protons and neutrons, they're in that really heavy, dense core, the nucleus. The last one we have is the electron. Electrons have a negative charge, so that's opposite of the proton. Protons are positive, electrons are negative. So every electron brings 1 negative charge to the atom. So 6 electrons, 6 negative charges. Now electrons are tiny, like all of this is small, but electrons are tiny, 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 so small that we say their mass, right, like their weight is negligible. Doesn't matter, we don't include it. So if we were looking at an atom, okay, when we look at atoms, there are a couple of things that we look at. We are going to look at the number of protons, neutrons, and electrons that are present. And the reason we do that is because we want to see the charge of the atom and the weight of the atom or size of the atom. So if we are looking at the mass, right, like the size, weight of the atom, we're going to do the number of protons plus the number of neutrons, because those are the 2 things that have mass. If we are going to look at the charge of the atom, okay, right, like positive, negative, neutral, the charge of the atom is going to be the number of protons, right, those are positive, minus the number of electrons, because electrons are negative. Right, so that, make sure you commit that to memory. Make sure you're able to do that, because we're going to use that kind of a lot as we go through the next few concepts. All right, I already mentioned this, but this is just the structure of an atom, right? So one atom has the nucleus in the middle. That's where the protons and neutrons are, the heavy stuff. And then the electron cloud contains the electrons orbiting around the nucleus. So each element has its own defining characteristics. So there are things that belong only to that element, right, that make that element special. That is the atomic number. So every element has its own atomic number. Okay, and that atomic number is important because it tells you the number of protons that are present in that element. So hydrogen, for example. Hydrogen is atomic number 1. That means that every atom of hydrogen has 1 proton. It's atomic number 1 means 1 proton. Every hydrogen in the world, no matter what, always has 1 proton. Trying to think what other ones did I know off my head. Carbon. Carbon is atomic number 6. That means that every atom of carbon has 6 protons. Okay, if it doesn't have 6 protons, it's not carbon. Okay, every carbon has 6 protons. That's what the atomic number tells us. Now, this number also tells us the number of electrons that the atom starts with. And the reason for this is that at the beginning, before anything happens, the atom is neutral. That means that the positives and the negatives cancel each other out. They have to be the same. So that means if the atom has 1 proton, it must also have 1 electron. Right? If it has 3 protons, it must have 3 electrons. Now, the number of electrons can change. And we'll see that. We'll look at that a lot throughout the lecture. But as atoms interact with each other, as they have chemical reactions and stuff happens, the number of electrons can change. The number of protons will never change. Okay, but to start, when we first look at the atom, the atomic number tells us the number of protons and the number of electrons that it's starting with. So when you guys look at the periodic table, you'll see again that each element has its own square. And in the middle of the square is the symbol. So for hydrogen, for example, the symbol is H. At the top, you'll see the atomic number. So we said hydrogen had an atomic number of 1. That told us the number of protons and the number of electrons that we're starting with. At the bottom of this box, you'll see the atomic weight. So down here for hydrogen, the weight is 1.00794. So like 1, right? About 1. Remember we said that the weight is that the heavy stuff, right, equals the number of protons plus the number of neutrons. So if we look at this right here, just the atomic number and the atomic weight, we can figure out for hydrogen how many protons, neutrons, and electrons are present, right? So for hydrogen, it has an atomic number of 1, so that means it has 1 proton and 1 electron. Now we need to find out how many neutrons. Well, I can find that by looking at the weight right here, right? If the weight equals, we're going to round that to 1, right? Remember we said that the weight of 1 equals protons plus neutrons. We already know that it has 1 proton, period. That's never going to change. So we'll just look at the math. 1 equals 1 plus 0. So hydrogen must have 0 neutrons. That's what normal hydrogen looks like, most hydrogen. 1 proton, 1 electron, 0 neutrons. So you can look at the periodic table and you can figure out how many protons, neutrons, and electrons an atom of that element is going to have. Now, each element has some different versions that might exist. Okay, so all hydrogen has 1 proton, right? And all hydrogen starts off with 1 electron. However, that different atoms of hydrogen can differ in the number of neutrons that they have. Okay, those are the different versions of hydrogen. We call these different versions isotopes. So isotopes are different versions of each element. And the versions differ based on their mass number, their overall mass, and their number of neutrons. Okay. So the mass number is different with the different isotopes, right? The weight is different. So some versions are a little bit heavier than others. Remember that the mass equals number of protons plus number of neutrons. Okay? different isotopes or different versions of an element, only the neutrons are different. The number of protons is not different because remember, the number of protons can't change. Okay, otherwise it's a different element. The number of protons is stable. So let's look at that. This is probably kind of confusing right off the top of your head. So let's look at some examples here. Remember, for hydrogen, if we looked at the periodic table, we would see H, we would see that it's atomic number 1, and we would see that the atomic mass is 1.00794. Most hydrogen that exists in the world looks like this. Most hydrogen has a mass number of 1. Okay, so hydrogen, it's atomic number 1, so we know that means it has 1 proton, 1 electron. If the mass, the total mass is 1, right, that means that it must have 0 neutrons. If you look at the picture, that's what it looks like, right? The middle, the nucleus has 1 proton with its positive charge. There's no neutrons there. And then you see this 1 negatively charged electron moving around in this electron shell. That's how most hydrogen is. Every once in a while in nature, very rare, but every once in a while in nature, you can find hydrogen that looks like this hydrogen 2. It's a heavy hydrogen. When we look at it, it's still atomic number 1, right? So it still has 1 proton and 1 electron. That didn't change. But when we look at this, look, this hydrogen has a mass number of 2. That means that it weighs 2 mass units, not just 1. And remember, the mass equals protons plus neutrons. So a mass of 2 equals, we know there's 1 proton and that's not changing, plus 1, right? There must be 1 neutron. So this heavy hydrogen here has 1 neutron. And you can see that in the middle, right? There's a proton and a neutron. So it's a little bit heavier. It has a larger mass because it has an extra neutron. Over here, you see another version of hydrogen. Okay, this is hydrogen 3. It's still hydrogen, so it still has the 1 proton here and the 1 electron. But its mass is 3, right? So that means it must have 2 neutrons. It's even heavier. Now, these heavy hydrogens are rare. These other isotopes are rare. Most hydrogen looks like this first one over here. This atomic mass that you see here on the periodic table, that's a weighted average of all the hydrogen that exists in the world. Okay, again, most only weighs 1. That's why this number is so close to 1, but it's not a whole number. Okay, that's why there's this little tiny decimal that exists here, because there is a very small amount of hydrogen that weighs 2 mass units. And then there's even less that weighs 3 mass units. So when you weigh it all, when you average it all together, you get an average of 1.00794. Okay, and you'll see that for, when you look at the periodic table, you'll see that for all of the elements, right? They're not whole numbers. They're close, but they're not whole numbers. And that's because there are different versions or different isotopes of each of the elements. All right, so we've been talking about the elements, right, in an atom. And we know that an atom has protons, neutrons, and electrons. And you guys know how to calculate how many of those there are, right, at the beginning. Now we know the number of protons in the atom is never going to change. That is stable, period. We just saw that the number of neutrons can be different in different versions different isotopes of the element. Now we're going to talk about electrons. right? And the way that the electrons can possibly change when the atom is interacting with another atom, okay, when chemical reactions are occurring. Now, you guys know the number of electrons that the atom is going to start with, right? It's the same as the number of protons because the atom starts out neutral with equal protons and electrons. But the atom doesn't have to stay that way. Hey, the number of electrons is not stable. The number of electrons that are present changes. Hey, that's how atoms interact with each other, is with their electrons. The reason for this is that atoms want to be stable, and atoms are most stable when their outermost electron shell, which we call their valence shell, is full. Okay, so electron shell, what's that? When we look at an atom, right, remember I told you guys that there's this dense nucleus in the middle, and that has the protons and protons and neutrons. And then we said that there's this electron cloud, and that's where the electron is floating around. Now, this electron cloud is actually a little more complicated than that. There are a series of shells or levels that are present in this electron cloud. Okay, so think of it kind of like floors in a house, right? You go into the first floor, but then you have stairs. You can exert some energy and use the stairs and go up to the second floor. And then you can spend more energy and use the stairs to go up to the third floor. That's how these electron shells are. There's the first shell, right? That doesn't take very much energy. But if you have too many electrons and you can't fit them in that first shell, then the electrons spend more energy to get out to the next shell. But if they fill up that one, then they've got to use more energy to go up to the next shell. So there are different shells or levels that are present in this electron cloud. The innermost shell, so the first shell that's really close to the nucleus, holds up to 2 electrons. That's it. The second shell and the third shell will hold up to 8 electrons. There are more shells than that. Some atoms are really big with a lot of electrons, but most atoms in humans are pretty small, so we're not going to go any further than that. We'll just do up to 3 shells. Okay, so you can put 2 electrons in the first shell, 8 in the second, 8 in the third. Now, atoms only have the number of shells that they need. They're not going to have like empty levels. So hydrogen has 1 electron, so it only has 1 shell, right? It just has the first shell here with its 1 little electron, and that's it. If it had 2 electrons, it would have 2 in that first shell. If it had 3 electrons, it would have 2 in the first shell, but then it would need another shell to put that third electron. Okay? So atoms, we said, are most stable when their outermost shell, their valence shell, is full. So hydrogen, for example, right, we said we had the nucleus, and then it has the first shell with just 1 electron. So its valence shell is that first shell, and it's not full, right? It can hold 2 electrons, and it only has 1. So hydrogen's not stable. Hydrogen really wants to fill that shell. It really wants to have another electron to put here in that shell. That's the reason atoms interact with each other. Hey, the reason they join together and build bigger things, right? The reason they form chemical bonds with each other is to try to fill their valence shell with the electrons. Okay, so a chemical bond is defined as the sharing, gaining, or losing of electrons to join atoms together to form a bigger unit, like a molecule or a compound. So you could have two separate atoms, right? I could have a hydrogen over here and a hydrogen over here. They're two small separate atoms. They form chemical bonds with each other. Okay, their outermost electrons interact with each other, right? And they form a chemical bond with each other. Now, instead of two separate things, I have one larger thing called a molecule. This is how atoms join. And we can have millions and millions of atoms joining together to form something large, like this, right? The table, myself, things that we can see and touch and feel. The major types of chemical bonds that exist are ionic bonds, covalent bonds, and hydrogen bonds. And we're going to talk through all of these. When chemical bonds form between atoms, so when you have a couple atoms that come together and bond with each other, they form a molecule or a compound. Okay. Molecules are defined as two or more atoms joined by strong bonds. You guys can actually cross out the strong bond, weak bond thing. I'm not worried about going into it that in depth. That's, if you take chemistry, you will. But so a molecule is two or more atoms joined by a bond. It doesn't matter what the atoms are. It doesn't matter. You could have two hydrogen bonded to each other. That's a molecule. You could have 6 atoms together. That's a molecule. It doesn't matter. As long as there are at least 2 atoms together, it's a molecule. A compound is a bit more complex. A compound is 2 or more atoms of different elements. So you have to have at least 2 different elements present to be a compound. So by that definition, all compounds are also molecules, okay, but not all molecules are compounds. So let's do an example. H2, that just means that there are 2 hydrogen atoms. So I have one hydrogen atom bonded to another hydrogen atom. That's a molecule, yes, because there are 2 atoms. But that is not a compound. There are 2 atoms, but they're not of different elements. There's only one element there. There's only hydrogen. Okay, how about H2O? That means that there are 2 hydrogen and 1 oxygen altogether. That's a molecule, yes, because it has at least 2 atoms. And that's a compound, yes, because we also have multiple elements. There's hydrogen and there's oxygen. Okay, so that meets both requirements. It could be something big, C6H12O6. That means there's 6 carbon, 12 hydrogen, 6 oxygen. That's glucose, like sugar. That's why I remember the formula, because we talk about it a lot. But that's a molecule. Yes, there's at least 2 atoms. That's a compound. Yes, there's 2 atoms and there's 3 different elements present. Okay. Okay, so we're going to start talking through the different type of bonds that exist. We'll probably just get through ionic bonds in today's lecture. But an ionic bond is just a bond between ions. An ionic bond is a bond between ions. Okay, what an ion is a charged atom. It can be positively charged or negatively charged, but it's an atom that has a charge. Remember, we said in the beginning, atoms are not charged, they're neutral because the number of protons and the number of electrons is the same and they cancel each other out. But it doesn't always have to be that way because the number of electrons can change. So if an atom gives away some of his electrons, or if he takes some more electrons, now the protons and electrons are not going to be balanced anymore, and the atom will be charged. Okay, that makes it an ion. Well, if you have a positively charged ion and a negatively charged ion, they will be attracted to each other because opposites attract. Okay, in chemistry, not just in the dating world, opposites attract. So the positive charge and the negative charge will pull together just like a magnet, and it'll hold those two atoms together to make a bigger structure. That's an ionic bond. So one of the atoms we refer to as the electron donor because he's the one who's getting rid of an electron. He's giving it away to the other one. So he loses one or more electrons. Remember, electrons are negatively charged. So if he's giving away those negative charges, overall, that atom is going to end up with a positive charge, right? He's getting rid of electrons, so he's going to end up with more protons than electrons. We call a positively charged ion a cation. The way I remember that is actually write it, and you'll see a big positive right in the middle. So cation, right? Positively charged. Now, the other atom that's involved, we call the electron acceptor because he accepts those electrons, right? So the donor is giving them away, the acceptor takes them. So that guy takes the electrons and he becomes an anion, which is a negatively charged ion. Again, opposites attract. So the positive and negative charges are attracted to each other. That holds those ions together, and we have something larger. Like, for example, sodium chloride, which is just table salt. That's an ionic compound. So we're going to see exactly how that happens here. And this will allow us to kind of put all of the concepts we've learned so far together. So make sure you work through this with me. We'll start with sodium. So sodium is atomic number 11. Okay, so if sodium is atomic number 11, which Na is the abbreviation. So try and remember that one because it doesn't make any sense, but Na means sodium. Sodium is atomic number 11. So that tells us that sodium has 11 protons, which remember are all positive, and it has 11 electrons, which are all negative. So let's place those 11 electrons. Remember, there are different little shells, right? The first one holds 2, second one holds 8, third one holds 8. So this first shell can hold 2 electrons, and you see them in these little yellow dots. So there's 1 electron, there's 2 electrons. Then we can put 8 in the next shell. 1, 2, 3, 4, 5, 6, 7, 8. So far we've put 10 electrons in. There's one more, right? Sodium has 11. So sodium must have a third electron shell, right? And it has just 1 electron in it. So remember that the whole point here is that the atoms want a full valence shell. They want a full outermost shell. Sodium has 1 out of 7. He is not happy. He's nowhere near being full, right? And it's going to be really hard to take 7 electrons from someone. It's not going to happen. So sodium will never fill up that third shell by stealing electrons. It's much easier for sodium to just give this 1 electron away. Because remember, they don't have empty shells. So if he gives that one electron away, this outer shell will be empty and the whole thing just disappears. And then what he's going to be left with is this full second shell. So sodium really wants to give one electron away. And that's exactly what happens here, right? This one electron disappears, and then if you move over here, that's what sodium ends up looking like. So when we look at whether it's charged or not, sodium still has 11 protons, right? That never changes. He has 11 protons, so 11 positives. But now he does not have 11 negatives anymore. He gave one of those electrons away. So now he only has 10 electrons or 10 negative charges. So remember, to get the overall charge, we do the number of protons minus the number of electrons. So 11 minus 10 equals 1, right? Plus 1. So now sodium has a plus 1 charge. That's why you see this little plus sign right here. And if you look up here, it says it's a sodium ion. And you see the little plus next to the symbol? That tells you that it's an ion. Now, chlorine. Chlorine is atomic number 17. So it has 17 protons, 17 electrons. Let's place those electrons. Okay. If you want to pause the video right now and put those 17 electrons in the shells to see if you can do it, go ahead and try and do it on your own. Remember, 2 electrons go in the first shell, 8 go in the second shell, so that's 10. That leaves us 7. So we put 7 in this third shell. The whole point is that he wants to fill up this third shell, so he needs 1 more to do it. Chlorine really wants 1 electron. So chlorine and sodium are perfect together. Sodium wants to give 1 away, chlorine wants to take it. So chlorine does. It takes that electron. And then if you move here to the second picture, this is what the chlorine looks like. Hey, chlorine becomes a chloride ion. Now it has a full third shell. It is happy. He's stable. Great. But he's no longer neutral. Right now he has 17 protons still, but he's got 18 electrons. He's got an extra electron. So to figure out the overall charge, remember it's the number of protons minus the number of electrons. So 17 minus 18 gives us -1. So chlorine is going to turn into a chloride ion with a -1 charge. So that's why you see this negative over here, negative. And if you look here, Cl for chlorine, and then it's got the little negative next to it. Remember, we said that opposites attract. So I have this ion that's positive and this ion that's negative, and those charges are pulled together. Instead of 2 separate ions, instead of a sodium over here and a chlorine over here, I now have a compound called sodium chloride, or table salt. A covalent bond is a bond that occurs when there's sharing of pairs of electrons between atoms. So the ionic bond, we had people taking electrons and giving electrons away. Covalent bonds, nobody's giving any electrons away. The 2 atoms come together and they share a pair of electrons. So 1 electron is donated by each atom to make the pair. So like this hydrogen is going to bring 1, this hydrogen is going to bring 1, and then they're going to share those 2. They're going to share that pair of electrons. Now you can share 1 pair of electrons, and that's called a single covalent bond. We draw that as 1 line. So like H, 1 line, H. This line shows us that they're sharing 1 pair of electrons. So there's like 2 electrons. Single covalent bond. Sharing 2 pairs of electrons is a double covalent bond. So we write that like that. Sharing 3 pairs is a triple covalent bond. We would write it like this. We're not going to really worry about that though. Double and single are the ones that we typically will see in humans. You guys don't have to really worry about like the more complex of these. I just want you to just kind of briefly understand the concept of what's happening here. So what you see here, H2 is a hydrogen molecule. So there are 2 hydrogen that are bonded together instead of 2 separate hydrogen. You see this one single line between them showing you that it's a covalent bond. And this shows you the actual model, like the actual electron shell model. Remember that each of these hydrogen has 1 electron. So there's this hydrogen that has 1, and then another one over here that has just 1 electron. They really want 2 electrons in that first shell. That would fill up the first shell. Now, a way that they can both be happy is if they come together and they form this molecule that you see here, where they're sharing that pair of electrons. So their electron shells kind of fuse with each other at this point. That's how they're bonded or attached. And remember, these electrons are constantly moving all over the place. So they spend some time on this side, some time on this side. They're always moving around. But both atoms have access to 2 electrons, so they're happy. Right? There's 2 electrons in this guy's shell. There's the same 2 electrons in this guy's shell. They're both satisfied. Now, these covalent bonds where atoms share electrons can be non-polar or polar. So there are 2 different types of covalent bonds. Non-polar covalent bonds occur when there's equal sharing of electrons. So that means that you have a balanced molecule. You're creating a balanced molecule or compound. This happens anytime you have 2 of the same thing sharing electrons. So if I have like hydrogen sharing electrons with hydrogen, that's going to be balanced, right? You have 2 of the same molecule. They're the same size. They're pulling on the electrons the same. They're sharing perfectly. So you end up with a balanced molecule, a non-polar molecule. However, sometimes there's a polar covalent bond. That happens when there's unequal sharing of electrons. So when you have this really big, strong molecule, and then you have this little one over here, the big, strong one will hog those electrons. So they're still sharing, but the electrons spend way less time with this little guy, and they spend way more time over here with this big guy. And what it creates is a molecule that's not balanced. It creates a polar molecule that has partial charges. Water is the classic polar molecule. Okay? The covalent bonds in water are polar. They're not even, they're not balanced. This picture up here shows us water. You have this big oxygen atom here, and then you have 2 little hydrogen atoms. Hey, there's a covalent bond right here between this hydrogen and the oxygen, and there's a covalent bond here between this hydrogen and the oxygen. Now, because the oxygen hogs these electrons, the electrons spend way more time over here, so this side of the water is more negative. The electrons spend way less time over here with the hydrogens, so they tend to be a little bit more positive. Now, these are not full charges like an ion. It's not a full charge. It's just like kind of charged. It's just a little bit charged, just a little unbalanced. Okay? This becomes really important because this allows us to have our next kind of bond, which is a hydrogen bond. Hydrogen bonds exist kind of like an ionic bond. You know how the ionic bond is the attraction between the positive and the negative charge? Well, a hydrogen bond is also an attraction between a positive and a negative. A hydrogen bond is the attraction between the slightly positive and slightly negative parts of polar molecules. So hydrogen bonds are bonds between molecules. They hold larger molecules together. The other bonds are bonds between atoms, right? So an ionic bond was sodium atom and a chloride atom being held together. Hydrogen bonds are molecules being held together. So like a whole water molecule and another whole water molecule that are attracted to each other. Polar molecules, remember we said, are formed when there are polar covalent bonds, right? They're non-balanced. So part of the molecule is positive, part of it's negative, right? So there are different poles, the negative pole and positive pole. So if you look here, you see hydrogen bonds. These are just water. There's a bunch of water. This red part is the oxygen, right? That's kind of negative. And these blue parts are the hydrogens that are kind of positive. And you see that the water molecules align themselves perfectly so that the positive from one is by the negative of the other. And these dotted lines are showing you the hydrogen bond. It's just a slight attraction that's present between the molecules. This is important. It's really important for the behavior of water and why water works the way that it does. These hydrogen bonds are responsible for surface tension in water. For example, like you know how a water bug can walk on water, or why like a leaf will float on the surface of water? That's because the water molecules have hydrogen bonds. They're attracted to each other. So the water molecules don't want to separate. Now, if you poke straight through, of course, you can separate it. The bonds aren't that strong, but there is some attraction between the water molecules. So water has surface tension. Or if you've ever filled up a glass of water, you fill it up really carefully, really slowly, and look right down at the top. You'll see that the water actually starts to go above the top of the rim before it falls over, because the water does have some attraction. The molecules are attracted to each other. They don't want to separate. Okay, so the fact that water is polar, meaning it has some charge, is very, very important to the behavior of water. Okay, guys, that was a whole lot for the day. We do have a good chunk of the lecture left, but I'm going to go ahead and wait. And I'm going to start here with the next lecture because I really want you to be able to look through and study the other stuff that we talked about to make sure that you really understand the concepts. Okay, so thank you for your patience with this lecture. It was late and it was a giant pain in the butt to try and get up. So thank you for your patience. Watch it this weekend, study, look ahead at this stuff if you want to, and then have a good weekend. And I will see you guys via video on Monday.